Approximately 115,000 years ago, subtle orbital shifts began reshaping the planet's climate system. These changes were not sudden catastrophes but gradual astronomical variations embedded within Earth's long-term orbital mechanics. Yet their cumulative effect altered global energy distribution enough to initiate one of the most significant climatic transitions of the Late Pleistocene. The beginning of the last glacial period is conventionally placed at the close of marine isotope stage 5e, the Eemian interglacial, dated to roughly 129,000 to 116,000 years before present. During MIS 5e, global temperatures were comparable to or slightly warmer than modern averages. Sea levels stood several meters higher than today, as indicated by coral reef terraces in the Bahamas and Mediterranean basin. However, by approximately 115,000 years ago, marine sediment cores show increasing ratios of oxygen, 18 isotopes, signaling the expansion of global ice volume. This isotopic shift marks the transition toward cooler conditions associated with marine isotope stage 4. The primary driver of this transition lies in cyclical variations in Earth's orbit, first mathematically described by Serbian geophysicist Milutin Milankovic in the early 20th century. These cycles include eccentricity, axial tilt, obliquity, and axial precession. Eccentricity alters the shape of Earth's orbit around the Sun on cycles of roughly 100,000 years. Obliquity, varying approximately every 41,000 years, changes the angle of Earth's axial tilt, influencing seasonal contrast. Precession, operating on roughly 19,000 to 23,000 year cycles, affects the timing of seasons relative to Earth's position along its orbit. Paleoclimatic reconstructions indicate that reduced summer insolation at high northern latitudes was the decisive factor in glacial initiation. When summer temperatures decline sufficiently, winter snow does not completely melt. Persistent snow cover increases surface reflectivity, or albedo, reducing absorption of solar radiation. This initiates a feedback mechanism. Cooler summers allow snow accumulation, increased reflectivity promotes further cooling, and snowfields gradually transition into ice sheets. Geological evidence from Scandinavia and northeastern Canada indicates early glacial nucleation in these regions during MIS 4. Ice core data provide further confirmation of atmospheric change. Greenland Ice Sheet Project, GRIP, and Greenland Ice Sheet Project 2, GISP2, cores reveal progressive temperature decline following the Eemian. Antarctic cores, including Epica Dome C, record decreasing concentrations of atmospheric carbon dioxide, falling from approximately 280 parts per million during interglacial conditions to lower levels as glaciation advanced. Records indicate that greenhouse gas decline amplified cooling already initiated by orbital forcing. Methane concentrations also dropped, reflecting reduced wetland extent and changing hydrological cycles. Marine sediment cores from the North Atlantic reinforce this chronology. Foraminifera shell isotopic analysis demonstrates increasing global ice volume after 115,000 years ago. These records correlate with glacial deposits identified in terrestrial stratigraphy across northern Europe. In regions such as the Alps, early glacial advances left moraines that correspond chronologically to MIS 4 cooling phases. The interaction between orbital forcing and atmospheric feedbacks demonstrates that glaciation did not begin as a singular event but as a gradual system-wide adjustment. Lower insolation weakened summer melting, declining greenhouse gases reinforced temperature reduction, expanding snowfields increased albedo, and ocean circulation patterns adjusted in response to freshwater input and cooling gradients. Climate models calibrated against paleo data confirm that orbital forcing alone is insufficient without feedback amplification, underscoring the interconnected nature of Earth's climate system. By approximately 100,000 years ago, the cooling trend had become firmly established. Ice accumulation accelerated in northern high latitudes, sea levels began to decline incrementally, and ecosystems gradually shifted in response to falling temperatures. Marine isotope records confirm that the planet had entered a sustained glacial trajectory that would persist, with fluctuations, for more than 100,000 years. Before continuing deeper into the chronology of the last ice age, viewers are encouraged to subscribe to the channel, activate notifications for daily Nightfall history releases, and share in the comments which section they find most informative to be why 30,000 years ago, ice sheets rivaled mountain ranges in scale. What had begun as persistent snowfields in high northern latitudes evolved into continental systems of ice spanning millions of square kilometers. These ice sheets did not advance uniformly. Rather, they expanded in pulses, responding to long-term cooling trends and shorter climatic oscillations recorded in marine and ice core data. Between approximately 100,000 and 70,000 years before present, glacial centers intensified in northeastern Canada and Scandinavia. Geological records indicate that ice accumulation first stabilized in elevated regions where snowfall exceeded summer melt. Over successive millennia, compaction transformed layered snow into glacial ice. As mass increased, gravity drove outward flow. Striated bedrock surfaces in Quebec and Finland preserve directional scoring patterns that confirm sustained southward movement. Moraines, ridges of debris deposited at glacial margins, mark successive advances and retreats, allowing reconstruction of icefront chronology. By marine isotope stage 4, around 71,000 to 57,000 years ago, major continental ice sheets had formed. In North America, the Laurentide ice sheet emerged as the dominant glacial body. Centered over present-day Hudson Bay, it expanded outward across much of Canada. To the west, the Cordilleran ice sheet developed along the mountainous spine of western North America. In northern Europe, the Fennoscandian ice sheet extended from the Scandinavian peninsula into the Baltic region and northern Germany. These systems grew independently but were shaped by similar climatic drivers: low summer insolation and sustained temperature decline. Ice thickness in central accumulation zones exceeded 3 kilometers, as indicated by glacial isostatic modeling and preserved pressure signatures in subglacial bedrock. Modern geophysical surveys of the Canadian Shield reveal depressed crustal surfaces still rebounding from glacial weight. Records indicate that the mass of these ice sheets was sufficient to lower the Earth's lithosphere by hundreds of meters. This crustal depression altered regional drainage systems and redirected river networks. As ice advanced southward, it reshaped continental topography. The Great Lakes Basin owes its configuration largely to glacial erosion. Ice scoured pre-existing river valleys, deepened basins, and deposited till across wide areas. In northern Europe, glacial movement carved fjords along the Norwegian coast and streamlined landscapes into drumlins and eskers. Sediment cores extracted from the North Atlantic contain layers of ice-rafted debris, coarse material transported by icebergs calved from continental margins, confirming marine interaction with expanding ice fronts. Sea levels fell progressively as freshwater became locked in continental ice. Coral reef terraces dated through uranium series methods indicate a decline of up to 120 meters below present levels by the height of glaciation. This regression exposed continental shelves and altered coastal configurations worldwide. The English Channel, for instance, periodically narrowed or became a fluvial valley system during lower sea stands. In Southeast Asia, the Sunda Shelf emerged, connecting mainland Asia to present-day Indonesia. By approximately 30,000 years ago, glacial expansion approached its maximum southern limits. The Laurentide ice sheet extended into what are now the northern United States, reaching present-day Illinois, Ohio, and New York in successive phases. In Europe, ice reached northern Germany and Poland, while the British Isles were largely covered, except for limited southern refugial zones. Radiocarbon dating of organic material beneath glacial tills confirms these advanced stages. Ocean circulation patterns responded to the growing ice mass. Freshwater input from melting margins influenced North Atlantic salinity gradients. Marine sediment data suggest fluctuations in thermohaline circulation, contributing to climatic variability recorded in Greenland ice cores. Increased albedo from expanded ice surfaces reinforced cooling, strengthening feedback loops already initiated by orbital forcing. The expansion of continental ice sheets was therefore not only a geological event but a planetary-scale restructuring of land, sea, and atmosphere. Through erosion, sediment redistribution, crustal depression, and sea level decline, glaciation reconfigured physical geography across the northern hemisphere. By the time the last glacial maximum approached, the cumulative effects of tens of thousands of years of ice growth had transformed continents into environments dominated by cold-adapted systems. Ice acted not only as a climatic force, but as a geological architect. Over tens of thousands of years, Continental glaciers reshaped the physical structure of the northern hemisphere, carving basins, redirecting rivers, and depositing sediments that continue to define modern landscapes. As ice sheets thickened and advanced, their immense weight exerted downward pressure on underlying bedrock. Glaciers move not as rigid blocks but as flowing masses, driven by gravity and internal deformation. As they advanced, embedded rock fragments acted as abrasive tools. This process, known as glacial abrasion, smoothed and polished bedrock surfaces. Parallel grooves and striations preserved across Scandinavia and the Canadian Shield provide clear directional evidence of ice movement. Archaeologists and geologists have documented these features extensively in northern Germany, Finland, and Quebec. In mountainous regions, valley glaciers transformed river-carved V-shaped valleys into broad U-shaped troughs. Across the European Alps, glacial erosion widened valley floors and steepened valley walls. Similar features appear in the Rocky Mountains of North America. The depth and uniform curvature of these valleys indicate prolonged glacial occupation rather than fluvial erosion alone. Radiometric dating of moraines in alpine regions confirms multiple advance and retreat cycles throughout marine isotope stages 4, 3, and 2. Along the Norwegian coastline, glacial erosion produced fjords. Deep, narrow inlets formed where glaciers carved below sea level. Modern bathymetric surveys reveal fjords extending hundreds of meters beneath present sea level. Sediment cores extracted from fjord basins contain layered deposits that correspond to glacial maxima and interstadial retreats. These records demonstrate that fjord formation was cumulative, shaped by repeated glaciations rather than a single advance. In North America, glacial activity reshaped entire drainage systems. The Great Lakes Basin represents one of the most prominent examples of large-scale glacial modification. Prior to extensive glaciation, river networks occupied much of this region. As the Laurentide ice sheet advanced, it deepened pre-existing depressions and scoured new basins. Geophysical surveys show that glacial erosion excavated bedrock channels, which later filled with meltwater as ice retreated. By approximately 10,000 years ago, proglacial lakes stabilized into the interconnected Great Lakes system observed today. Repeated cycles of advance and retreat left behind extensive depositional features. Moraines mark the furthest reach of ice margins during specific intervals. Ground till unsorted sediment deposited directly beneath glacial ice, blanketed wide regions of northern Europe and the American Midwest. These deposits altered soil composition and influenced later agricultural productivity. In some regions, glacial till forms the foundation of modern plains. Wind-driven processes also intensified during glacial periods. Vast quantities of fine sediment were produced by glacial grinding. As meltwater rivers dried seasonally and vegetation cover diminished, strong winds transported silt across continents. These deposits accumulated as loess, forming thick sediment layers in Central Europe and the Chinese loess plateau. In China, loess sequences exceeding 300 meters in thickness preserve alternating paleosols and dust layers, providing a continuous climatic record spanning multiple glacial cycles. Optically stimulated luminescence dating confirms deposition peaks during colder, drier intervals. Glacial meltwater further reshaped continental interiors. As ice sheets retreated episodically, meltwater accumulated along their margins, forming proglacial lakes. Lake Agassiz, which developed along the southern margin of the Laurentide ice sheet, covered areas of present-day Manitoba, Ontario, and North Dakota. At its maximum extent around 12,000 years ago, it was larger than any modern freshwater lake. Shoreline terraces and sedimentary sequences confirm fluctuating water levels linked to shifting ice barriers. Periodic drainage events released massive volumes of freshwater into the North Atlantic, influencing ocean circulation. The cumulative effect of these processes was a reorganization of continental topography. River systems such as the Mississippi and the Rhine adjusted to new sediment loads and drainage patterns. Isostatic depression beneath heavy ice masses altered elevation gradients, while subsequent rebound continues today in regions such as Scandinavia and Canada. GPS measurements confirm that some formerly glaciated areas are still rising several millimeters per year. The landscapes of the northern hemisphere therefore bear direct evidence of prolonged glacial engineering. Fjords, lakes, lush plains, and reshaped valleys represent material records of ice movement sustained over tens of thousands of years. These features demonstrate that glaciation functioned not only as a climatic phase but as a transformative geological force. In many regions, cold meant dryness rather than snow. Although continental ice sheets dominated higher latitudes during the last ice age, vast portions of the subtropics and mid-latitudes experienced a different transformation. Cooler global temperatures altered atmospheric circulation, shifting storm tracks and weakening monsoon systems. The result was not uniform freezing, but widespread aridity. Deserts expanded, grasslands contracted, and hydrological systems reorganized across Africa and Eurasia. Lower global temperatures reduced overall evaporation rates from the oceans. Yet the key driver of aridity was not simply temperature decline. Instead, it was the redistribution of precipitation. As ice sheets grew, they modified planetary-scale pressure systems. The polar front shifted southward, and the jet stream altered its trajectory. Regions that once received seasonal rainfall found themselves positioned beneath descending, dry air masses. The Sahara provides one of the clearest examples of glacial aridity. Today, the Sahara is already the largest hot desert on Earth, but during cold phases of the Late Pleistocene it expanded significantly beyond its present boundaries. Pollen records extracted from sediment cores in the Mediterranean indicate a reduction in tree and grass taxa across North Africa during glacial maxima. Simultaneously, increased dust deposition in Atlantic marine cores reflects intensified wind erosion from exposed desert surfaces. Lake sediment evidence supports this reconstruction. Basins that today contain remnants of paleolakes, such as those in Chad and Libya, show fluctuating water levels corresponding to climatic cycles. During interglacial humid periods, freshwater lakes expanded, supporting savanna ecosystems. During glacial maxima, however, many of these lakes contracted dramatically or disappeared altogether. Evaporite deposits and shoreline terraces document these oscillations. Reduced rainfall weakened river systems feeding the Sahara's interior basins, fragmenting habitable zones. Monsoon dynamics played a central role in these changes. The African monsoon depends on seasonal heating contrasts between land and ocean. During glacial periods, lower temperatures diminished this thermal gradient. Additionally, extensive ice sheets increased planetary albedo, reflecting more solar radiation and further weakening monsoon circulation. As a result, summer rainfall across the Sahel declined, shifting vegetative zones southward. Grasslands retreated, and hyperarid conditions extended deeper into the continent. Central Asia experienced comparable transformations. Evidence from lush sequences and pollen cores across Kazakhstan and western China indicates expanded steppe and desert conditions between approximately 70,000 and 20,000 years ago. The weakening of the Asian summer monsoon reduced precipitation across interior basins such as the Darim and Gobi regions. Increased dust flux recorded in Chinese loess layers confirms stronger winds and diminished vegetation cover. These deposits provide high-resolution records of glacial stage aridity. Hydrological systems across Eurasia responded accordingly. Rivers dependent on monsoonal input experienced reduced discharge. In some regions, proglacial meltwater temporarily augmented river systems, but beyond the influence of ice margins, water scarcity intensified. Endorheic basins, closed drainage systems without ocean outlets, became increasingly saline as evaporation exceeded inflow. Sediment cores from the Caspian and Aral basins reveal fluctuations in water level linked to broader climatic shifts. The Mediterranean basin also reflects these environmental adjustments. Speleothem isotopic records from caves in southern Europe show decreased precipitation during peak glacial intervals. Vegetation reconstructions indicate a shift toward open woodland and steppe environments in regions that today support denser forest cover. Although Europe remained cooler overall, moisture availability varied significantly between western maritime zones and continental interiors. These patterns illustrate a broader principle of glacial climate. Cold conditions do not necessarily imply widespread snowfall. Precipitation requires atmospheric moisture, and colder oceans reduce evaporation. With less water vapor available, many subtropical regions became drier even as polar and high-altitude zones accumulated ice. The ecological consequences were substantial. Vegetation zones reorganized across continents. Grasslands expanded in some mid-latitude belts, while deserts widened in subtropical regions. Forest biomes fragmented into refugia, isolated pockets where conditions remained suitable for tree survival. Genetic studies of modern plant populations confirm bottleneck events consistent with contraction into these refugial zones during glacial maxima. These environmental changes also shaped human geography. Arid corridors limited migration routes across North Africa and Western Asia. During humid interstadials, expanded river systems and lakes created habitable pathways linking sub-Saharan Africa to the Levant. During arid phases, these corridors narrowed or vanished. Archaeological site distributions across the Sahara reflect this pattern. Concentrations cluster near Paleolake margins during wetter intervals and decline during peak aridity. In Central Asia, fluctuating steppe and desert boundaries influenced the movement of Paleolithic populations. Open grasslands supported grazing megafauna, while hyperarid deserts restricted sustained occupation. Human settlement patterns track the shifting availability of freshwater and game animals. Similarly, in the Near East, reduced precipitation altered river discharge in the Tigris and Euphrates systems, influencing resource distribution for early human groups. Atmospheric dust increased globally during glacial periods. Ice cores from Greenland and Antarctica show elevated dust concentrations corresponding to expanded desert surfaces. These particles influenced climate feedback mechanisms by affecting radiative balance and nutrient transport to oceans. Iron-rich dust deposited into marine environments may have stimulated phytoplankton growth, indirectly affecting carbon cycling. By the last glacial maximum around 21,000 years ago, the Earth's climate system exhibited sharp contrasts. Vast ice sheets in high latitudes, extensive deserts in subtropical belts, and reorganized vegetation zones in between. The redistribution of moisture redefined ecosystems and constrained biological communities. These climatic and ecological transformations did not occur in isolation. As habitats shifted, animal populations adapted, migrated, or declined. The changing balance between cold, dry steppes and fragmented forests reshaped the distribution of megafauna across Eurasia and the Americas. For tens of thousands of years, a vast grassland stretched across the northern continents. Between approximately 60,000 and 20,000 years ago, much of Eurasia and North America was dominated by a cold, dry, and highly productive ecosystem known as the mammoth steppe. Unlike the modern Arctic tundra, which is characterized by low biodiversity and waterlogged soils, the mammoth steppe supported dense herbivore populations across an immense transcontinental belt. This biome extended from the Iberian Peninsula across Central Europe and Siberia, crossed the exposed Bering Land Bridge, and continued into Alaska and the Yukon. It constituted one of the largest continuous terrestrial ecosystems of the Late Pleistocene. Climatic conditions during this interval were cold but relatively stable. Precipitation levels were generally low, particularly during peak glacial phases, yet they were sufficient to sustain grasses and herbaceous plants adapted to arid environments. Crucially, low atmospheric CO2 concentrations, approximately 180 to 200 parts per million during glacial maxima, favored plant species capable of efficient carbon uptake under such constraints. Grasses and sedges, many employing C3 photosynthetic pathways adapted to cool climates, dominated the landscape. Paleoecological evidence supports this reconstruction. Pollen cores extracted from loess deposits in Ukraine, southern Siberia, and Eastern Europe consistently reveal high proportions of grass, Poaceae, and sedge, Cyperaceae pollen. Arboreal pollen percentages decline significantly in these sequences, indicating the absence of dense forests across large areas. Plant macrofossils preserved in permafrost further confirm the prevalence of herbaceous vegetation, including artemisia, sagebrush, and other drought-tolerant taxa. Loess-rich soils played a central role in sustaining productivity. As glaciers ground bedrock into fine particles, winds transported silt across mid-latitude regions. This material accumulated in thick deposits across Europe, Central Asia, and parts of North America. Loess soils are mineral-rich and well-drained, conditions that favor grassland ecosystems. Even with limited rainfall, these soils retained sufficient nutrients to support extensive grazing. The mammoth steppe differed structurally from modern tundra in another important way. It lacked widespread peat formation. Today's tundra is often waterlogged due to permafrost limiting drainage. During the late Pleistocene, colder and drier conditions reduced surface moisture, preventing the development of extensive wetlands. Instead, well-drained soils supported continuous grass cover across vast plains. This combination of aridity, cold temperatures, and fertile sediment created an environment capable of sustaining high herbivore biomass. Stable isotope analysis of megafaunal remains provides additional confirmation. Ratios of carbon and nitrogen isotopes preserved in the bones and teeth of woolly mammoths, Mammuthus primigenius, woolly rhinoceroses, Coelodonta antiquitatis, and steppe bison indicate diets dominated by grasses rather than browse from shrubs or trees. These isotopic signatures are consistent across specimens recovered from sites stretching from Western Europe to Eastern Siberia and into Beringia. Dental microwear patterns also align with grazing behavior, showing abrasion typical of grass consumption. The geographic scale of the mammoth steppe was unprecedented in the modern era. During periods of lowered sea level up to 120 meters below present, the Bering Land Bridge connected Siberia and Alaska. This landmass was not merely a migration corridor but part of the broader steppe ecosystem. Fossil assemblages from Alaska and Yukon contain species nearly identical to those found in northeastern Siberia, indicating ecological continuity across continents. This biome supported a diverse assemblage of large herbivores. Woolly mammoths, adapted to cold conditions with thick fur and subcutaneous fat layers, roamed in herds across open plains. Woolly rhinoceroses occupied similar habitats. Their wide, flat horns possibly used to clear snow and access vegetation. Steppe bison, Bison priscus, formed substantial herds, while reindeer, Rangifer tarandus, migrated seasonally across grasslands and uplands. Horses of the genus Equus also thrived in these open environments. Predators followed the distribution of prey. Cave lions, Pantherospelea, wolves, Canis lupus, and scimitar-toothed cats inhabited the same regions, forming complex trophic networks. The density of herbivore populations suggests that primary productivity in the mammoth steppe exceeded that of modern Arctic systems. Modeling studies based on carrying capacity estimates indicate biomass levels comparable to some contemporary African savannas, despite much colder temperatures. The persistence of the mammoth steppe was closely tied to glacial climate stability. During prolonged cold phases, reduced precipitation limited forest expansion. Low CO2 concentrations may have suppressed tree growth, giving competitive advantage to grasses. As long as these atmospheric and climatic conditions remained in equilibrium, the steppe biome remained dominant. However, this ecosystem was sensitive to rapid climate transitions. During interstadial warming events recorded in Greenland ice cores, tree pollen percentages increase in some European sequences, indicating forest encroachment. These episodic changes foreshadowed the more substantial transformations that would occur at the end of the last glacial maximum. For tens of thousands of years, the mammoth steppe provided the ecological foundation for Ice Age megafauna and for human hunter-gatherer populations who depended on them. Its vast grasslands linked continents, supported high animal densities, and shaped evolutionary trajectories across the northern hemisphere. The Ice Age landscape was defined by animals weighing several tons. Across the mammoth steppe and adjacent environments of the late Pleistocene, megafauna occupied a central ecological role. These large-bodied mammals, many exceeding 1,000 kilograms, were not marginal inhabitants of a harsh world, but dominant components of stable and productive ecosystems. Their anatomical adaptations, fossil distribution, and ecological influence reveal an integrated system shaped by cold climates and expansive grasslands. Physiological specialization allowed these animals to thrive in environments characterized by low temperatures and seasonal resource scarcity. Woolly mammoths, Mammuthus primigenius, possessed dense underwool beneath long guard hairs, forming an insulating coat capable of retaining heat in sub-zero conditions. Subcutaneous fat layers provided additional thermal protection and energy storage. Small ears and short tails reduced surface area to volume ratios, minimizing heat loss in accordance with Bergmann's and Allen's ecological rules. Similar traits appear in the woolly rhinoceros, Coelodonta antiquitatis, whose fossilized remains preserve impressions of thick fur. Direct anatomical evidence comes from frozen carcasses recovered in Siberian permafrost. The Berezovka mammoth, discovered in 1901 along the Berezovka River, remains one of the most well-documented specimens. Its preserved musculature, stomach contents, and skin confirmed grazing diets and cold-adapted morphology. Subsequent discoveries, including juvenile mammoths and steppe bison preserved in permafrost, have reinforced these findings. Tissue analysis reveals well-developed fat reserves and structural adaptations consistent with long-term survival in cold, dry steppe environments. Radiocarbon dating of megafaunal remains indicates peak abundance between approximately 40,000 and 25,000 years ago. During this interval, the mammoth steppe biome reached maximum spatial extent and ecological stability. Fossil assemblages from Siberia, Eastern Europe, and Beringia demonstrate high population densities of mammoths, steppe bison, bison priscus, horses, equus ferus, reindeer, Rangifer tarandus, and woolly rhinoceroses. These herbivores formed the primary trophic base of late Pleistocene ecosystems. Large predators occupied parallel ecological niches. Cave lions, Pantherospelea, larger than most modern African lions, ranged across Europe and northern Asia. Their remains appear in cave deposits and open-air sites, often associated with herbivore bone assemblages. Dire wolves, Canis dirus, documented extensively in North America, coexisted with gray wolves and other carnivores. Fossil evidence from the La Brea tar pits in California provides detailed insight into predator-prey dynamics. Thousands of recovered specimens, including saber-toothed cats, Smilodon fetalis, dire wolves, and herbivores such as bison and camels, indicate complex food webs structured around large grazing mammals. The La Brea assemblage also illustrates behavioral ecology. High predator representation suggests that carnivores were attracted to trapped prey, becoming ensnared themselves. This concentration of species provides a rare snapshot of late Pleistocene faunal communities in western North America. Comparative analysis of tooth wear and bone trauma patterns indicates active predation rather than exclusive scavenging. Megafaunal herbivores were not passive occupants of their environment. Their grazing pressure significantly influenced vegetation structure and biome stability. Mammoths, for example, consumed large quantities of grasses and shrubs, suppressing woody plant encroachment. Modeling studies and modern analog experiments suggest that sustained grazing maintained open grassland conditions, reinforcing the mammoth steppe biome. In regions where megafaunal populations declined, paleoecological records often show subsequent increases in shrub and tree pollen, implying a shift in vegetation structure. Trampling and nutrient redistribution further altered landscapes. Large herbivores compacted soil, dispersed seeds, and deposited dung that fertilized grasslands. These processes enhanced primary productivity and contributed to the persistence of open steppe ecosystems. The interaction between climate, vegetation, and megafauna thus formed a feedback system. Cold and dry conditions favored grasses. Grasses supported large herbivores. Herbivores maintained grass dominance. Human populations increasingly intersected with these ecological networks. Archaeological evidence indicates that anatomically modern humans spread across Eurasia between 45,000 and 35,000 years ago, entering landscapes already inhabited by megafauna. Sites such as Dolní Věstonice in the Czech Republic provide clear evidence of human megafauna interaction. Mammoth bones recovered from this Gravettian settlement display cut marks consistent with systematic butchery. Some mammoth bones were used structurally, forming dwelling frameworks. Radiocarbon dating situates this site around 30,000 years ago, within the interval of peak megafaunal abundance. Stable isotope analysis of human remains from Upper Paleolithic contexts indicates diets heavily reliant on large herbivores. Nitrogen isotope ratios suggest high trophic level consumption, consistent with regular intake of mammoth, bison, and reindeer meat. This dietary specialization implies a close ecological relationship between human groups and megafaunal populations. Predator guilds adapted alongside herbivores and humans. Competition for prey may have intensified as human hunting efficiency improved. However, during the peak glacial interval, megafaunal populations appear robust and geographically widespread. Fossil distribution patterns do not indicate abrupt declines prior to the last glacial maximum. Physiological resilience, ecological dominance, and geographic continuity characterized these species for tens of millennia. Yet their survival was contingent on the stability of the mammoth steppe and the climatic conditions that sustained it. As atmospheric circulation patterns shifted and temperatures began to rise toward the end of the last glacial maximum, environmental pressures would intensify. Long before modern humans dominated Eurasia, another human species thrived in the cold. Neanderthals, Homo neanderthalensis, occupied Europe and parts of Western Asia from approximately 400,000 until around 40,000 years ago. Their evolutionary trajectory unfolded during repeated glacial and interglacial cycles of the Middle and Late Pleistocene. Far from being marginal survivors, Neanderthals were highly adapted to the fluctuating and often severe climates of glacial Europe. Anatomically, Neanderthals displayed traits consistent with cold adaptation. Their bodies were robust and compact, with relatively short distal limb segments, features that reduce heat loss in cold environments. Broad nasal cavities may have aided in warming and humidifying cold air before it reached the lungs. Skeletal remains from sites such as La Pharisee in France and Vindija Cave in Croatia reveal thick cortical bone and strong muscle attachment sites, indicating physically demanding lifestyles consistent with close-range hunting. During colder marine isotope stages, particularly MIS-4 and MIS-2, much of northern Europe was covered by ice sheets or periglacial environments. Neanderthals generally occupied regions south of major ice margins but still within cold steppe and open woodland ecosystems. Archaeological evidence suggests strategic settlement choices, often near river valleys, rock shelters, or areas with access to migratory herbivore routes. Neanderthal technological adaptation is most closely associated with the Mousterian tool industry, characterized by prepared core techniques such as the Levallois method. This approach allowed for controlled production of flake tools with predictable shapes and cutting edges. Mousterian assemblages appear widely across Europe and Western Asia, reflecting a shared technological tradition with regional variation. These tools were effective for butchering large animals, scraping hides, and woodworking. Faunal remains at numerous Neanderthal sites indicate a heavy reliance on large herbivores. Stable isotope analysis of Neanderthal bone collagen shows elevated nitrogen isotope values, placing them high on the trophic scale. In many regions, their diet was dominated by species such as reindeer, red deer, horse, and steppe bison. At La Pharisee and other southwestern French sites, cut marks on bones demonstrate systematic butchery and marrow extraction. Evidence from isotope studies suggests that Neanderthals consumed animal protein at levels comparable to apex predators. Hunting strategies appear to have involved close-range thrusting spears rather than projectile weapons. Wooden spears recovered from earlier sites such as Skåningen, attributed to Homo heidelbergensis, a likely ancestor, demonstrate a long-standing tradition of large-game hunting in Europe. Neanderthals likely continued and refined these methods. Skeletal trauma patterns on Neanderthal remains, similar to injuries seen in modern rodeo riders, support the interpretation of frequent close encounters with large prey. Occupation patterns indicate flexibility. During colder phases, populations appear to have contracted into refugial zones in southern Europe, including the Iberian Peninsula, Italy, and the Balkans. During milder interstadials, Neanderthals expanded northward. This cyclical distribution corresponds with climatic oscillations recorded in Greenland ice cores. Cultural evidence also suggests social complexity. Burials at La Pharisee include individuals placed in shallow graves, possibly indicating mortuary practices. While interpretations remain debated, the deliberate positioning of bodies implies symbolic or social behavior. At Vindija Cave, Fragmentary remains dated to approximately 40,000 years ago represent some of the last known Neanderthal populations. The sequencing of the Neanderthal genome in 2010 fundamentally altered understanding of their relationship to modern humans. Genetic evidence confirms that Neanderthals interbred with Homo sapiens after the latter dispersed out of Africa. Today, non-African human populations retain approximately 1 to 2% Neanderthal DNA. This admixture indicates not only biological compatibility but periods of direct interaction across Eurasia. Despite their adaptability, Neanderthals disappeared around 40,000 years ago. The causes remain debated and likely multifactorial, involving climatic instability during late glacial fluctuations, competition with expanding modern human populations, and demographic vulnerability in small, dispersed groups. Importantly, their extinction does not reflect an inability to survive cold conditions. For hundreds of thousands of years, Neanderthals successfully inhabited glacial and periglacial landscapes. Their presence in Ice Age Europe demonstrates that archaic humans possessed both physiological and technological means to endure extreme environments. Through cooperative hunting, strategic settlement, and adaptive toolmaking, they occupied ecological niches shaped by shifting ice margins and expanding steppe ecosystems. In Asia, another archaic lineage evolved under similar pressures. A fragment of bone revealed a previously unknown human lineage. In 2008, excavations at Denisova Cave in the Altai Mountains of southern Siberia uncovered a small finger bone fragment from a juvenile individual. Morphologically, the specimen offered limited diagnostic information. However, advances in ancient DNA extraction and sequencing allowed researchers to analyze its genome. The results demonstrated that the individual did not belong to either Neanderthals or modern humans, but to a previously unidentified archaic population now known as the Denisovans. Genetic analysis indicates that Denisovans diverged from a common ancestor shared with Neanderthals approximately 400,000 to 500,000 years ago. Although fossil evidence remains sparse, consisting primarily of fragmentary bones and teeth from Denisova Cave and a mandible identified on the Tibetan Plateau, their genetic footprint is substantial. Unlike Neanderthals, whose skeletal remains are widespread across Europe and Western Asia, Denisovans are primarily known through genomic data. Denisovan DNA has been detected in modern human populations across parts of Asia and Oceania. Indigenous groups in Melanesia and Papua New Guinea carry the highest proportions, in some cases up to 4 to 6% Denisovan ancestry. Smaller but detectable contributions appear in East Asian and Southeast Asian populations. These findings indicate multiple episodes of interbreeding between Denisovans and anatomically modern humans after Homo sapiens dispersed into Eurasia. One of the most significant discoveries linked to Denisovan genetics involves adaptation to high-altitude environments. Modern Tibetan populations possess a variant of the EPAS1 gene associated with efficient oxygen utilization under hypoxic conditions. Comparative genomic analysis shows that this variant closely matches Denisovan sequences rather than those typical of other modern human populations. This suggests that interbreeding introduced a beneficial allele into the ancestors of present-day Tibetans, facilitating long-term habitation at elevations exceeding 4,000 meters. The Denisovan mandible discovered at Baishia Karst Cave on the northeastern Tibetan Plateau provides additional insight. Uranium series dating places the specimen at over 160,000 years old, indicating that Denisovans occupied high-altitude regions long before modern humans arrived. Protein analysis confirmed its Denisovan affiliation despite limited DNA preservation. This evidence demonstrates physiological and behavioral adaptation to cold, oxygen-poor environments during the Middle Pleistocene. Chronologically, Denisovans overlapped with both Neanderthals and early Homo sapiens. Genetic data suggests periods of contact among these groups. Some Denisovan genomes exhibit traces of Neanderthal admixture, implying interaction between archaic populations in Eurasia prior to the arrival of modern humans. The Altai region may have functioned as a contact zone where multiple hominin groups intersected over tens of thousands of years. Archaeological material from Denisova Cave includes stone tools and ornamental artifacts spanning different occupation layers. However, direct association between specific tool industries and Denisovan individuals remains uncertain. The cave contains deposits attributed to Neanderthals, Denisovans, and modern humans at different times, complicating cultural attribution. Nevertheless, the repeated occupation of this site indicates its strategic importance within Ice Age landscapes. Environmental conditions in southern Siberia during the Late Pleistocene fluctuated between cold steppe and forest steppe systems. Denisovan survival in this region implies flexibility comparable to that of Neanderthals. Their geographic distribution, inferred from genetic traces, likely extended across large parts of Eastern Asia. However, limited fossil recovery constrains precise mapping of their range. The discovery of Denisovans underscores the transformative impact of genetic archaeology. Prior to genomic sequencing, no clear morphological category existed for this lineage. Their identification demonstrates that the late Pleistocene human landscape was more diverse than previously recognized. Rather than a simple replacement of archaic humans by modern humans, Eurasia appears to have hosted overlapping populations that exchanged genes and, potentially, cultural knowledge. The persistence of Denisovan genetic contributions in modern populations suggests that admixture conferred adaptive advantages in certain environments. High-altitude adaptation in Tibet represents one documented case, but other gene variants related to immune function and environmental resilience may also derive from Denisovan ancestry. Despite these insights, the reasons for Denisovan disappearance remain uncertain. As with Neanderthals, extinction likely involved a combination of climatic instability, demographic pressures, and competition with expanding modern human groups. By approximately 40,000 years ago, Denisovans no longer appear as a distinct population in the fossil or genetic record, though their legacy survives within modern genomes. Around 70,000 years ago, Homo sapiens began expanding beyond Africa. Around 45,000 years ago, toolmaking entered a new phase of precision and specialization. During the Upper Paleolithic, roughly spanning 50,000 to 30,000 years ago, technological innovation accelerated across Eurasia. The Middle Paleolithic Mousterian industries, characterized by prepared core flake tools primarily associated with Neanderthals, gradually gave way to blade-based lithic technologies. The aurignation industry, emerging around 43,000 years ago, is one of the earliest examples, featuring long, standardized blades produced from carefully prepared cores. Sites such as Abri-Pitaud in southwestern France provide stratified evidence of these technological advances, including refitting studies that document methodical flake removal and tool preparation. Following the aurignation, the Gravettian industry, c. 30,000 to 22,000 BP, demonstrates further diversification. Archaeological layers at Kostenki in western Russia contain well-preserved blade and burin assemblages, along with bone and antler tools. These include projectile points, awls, and needles, reflecting increasingly sophisticated strategies for clothing and hunting adaptation to cold environments. The Solutrean industry, c. 22,000 to 17,000 BP, in southwestern Europe exhibits even higher degrees of specialization, with finely pressure-flaked points and bifacial implements indicating meticulous craftsmanship. Microlithic refinement contributed to improved hunting efficiency. Composite tools combining stone points with wooden shafts or antler inserts allowed humans to exploit megafaunal prey at greater distances and with enhanced lethality. Bone and antler artifacts, including sewing needles, indicate tailored clothing production, essential for survival in glacial conditions. Such technological solutions suggest advanced planning, manual dexterity, and cognitive innovation. Radiocarbon dating across European sites confirms rapid dissemination of these technologies. The chronological overlap of aurignation and Gravettian industries, coupled with the standardization of tool forms, implies widespread knowledge transmission within expanding social networks. Artifacts indicate that groups were capable of producing functionally consistent toolkits across hundreds of kilometers, suggesting interaction or shared cultural frameworks. Technological diversification reflects not only functional adaptation but cognitive development. The production of standardized blades, composite tools, and sewn garments required sequential planning, problem-solving, and abstract understanding of material properties. Such capabilities indicate a significant evolution in human behavior compared to earlier hominin populations. Material evidence also suggests that toolkits were adapted to environmental constraints. The cold, dry conditions of the mammoth steppe required both efficient hunting strategies and protective clothing. Bone and antler tools supported both objectives, while lithic refinement allowed for conservation of raw material in regions where suitable stone was scarce. These adaptations reveal a close relationship between technological innovation and ecological pressures. The emergence of standardized and complex tools coincides with population expansion. Higher mobility and broader geographic ranges necessitated versatile, transportable toolkits. Archaeological patterns suggest that communities maintained shared technological knowledge across multiple generations. This continuity indicates structured teaching and learning processes within groups, supporting cumulative cultural evolution. Additionally, archaeological layers frequently contain evidence of repeated occupation and site maintenance, suggesting planning, logistical foresight, and seasonal scheduling. Tool caches and specialized manufacturing areas, such as those observed at Abripatad, imply coordinated group activity and division of labor. These patterns support the inference of complex social organization emerging alongside technological sophistication. By the end of the Upper Paleolithic technological transition, humans had established the material foundation for symbolic and cultural expression. The systematic production of blades, burins, and composite implements not only facilitated survival in harsh Ice Age environments, but also enabled greater flexibility for social and symbolic behaviors. Deep within Ice Age caves, humans recorded images of the world around them. By approximately 40,000 years ago, anatomically modern humans were producing figurative representations of their environment. The earliest confirmed examples of cave art are found at sites such as Chauvet Cave in southern France and Sulawesi in Indonesia. Uranium-thorium dating of calcite overlying painted surfaces confirms ages exceeding 36,000 years, establishing that symbolic visual expression emerged early in Upper Paleolithic societies. These paintings frequently depict megafauna characteristic of the mammoth steppe and surrounding environments. Horses, aurochs, mammoths, and bison appear with careful attention to proportion, perspective, and implied movement. Line variation, shading, and engraved outlines suggest deliberate techniques intended to convey depth and vitality. Such representations reflect not only observational skill but also an ability to abstract and communicate complex visual information. Caves often contain non-figurative motifs as well. Hand stencils, geometric patterns, and dot arrangements appear in spatially organized sequences. The recurring placement of these motifs deep within galleries, often in areas inaccessible without artificial lighting, suggests intentionality and perhaps ritual significance. Archaeologists have proposed that these designs may have functioned as markers of territory, teaching tools, or components of shared cosmologies. Portable art further demonstrates the spread of symbolic behavior beyond permanent shelters. Objects such as the Venus of Willendorf, dated to approximately 28,000 to 25,000 BP, depict stylized human forms. Carved from limestone or bone, these figures emphasize fertility features, suggesting shared cultural or social narratives. The distribution of similar figurines across Europe and Western Asia indicates the widespread adoption of symbolic conventions. Material preparation underscores the deliberate nature of these artistic practices. Pigment analysis reveals that ochre and charcoal were selected, ground, and mixed to create stable colorants. Traces of binders such as animal fat or plant extracts have been identified, suggesting an understanding of material properties and intentionality in medium preparation. Brush marks, finger smears, and engraved outlines reflect diverse techniques applied with skill and planning. Stratigraphic studies at sites like Lascaux, c. 17,000 BP, and Altamira, c. 14,000 BP, demonstrate continuity and refinement in cave art traditions. Later works exhibit enhanced perspective, layering, and dynamic composition, indicating an evolving visual vocabulary. The coexistence of portable and fixed art suggests that Upper Paleolithic humans maintained symbolic practices across multiple contexts, integrating them into both domestic and ceremonial spaces. Spatial analysis of cave galleries indicates selective placement of images, often in acoustically resonant chambers or deep galleries with limited light penetration. Experimental archaeology confirms that torches and lamps were necessary for access, implying intentional site preparation and complex planning. Such placement may reflect ritual behavior, storytelling, or mnemonic devices to transmit knowledge within and between groups. Collectively, these practices provide compelling evidence for abstract thinking, shared belief systems, and cognitive complexity. Cave art demonstrates that humans were capable of intentional representation, symbolic communication, and the codification of social or cosmological ideas. The integration of visual symbolism into daily and ceremonial life suggests that art functioned as a central component of social cohesion and cultural identity. Within millennia, modern humans occupied nearly all of Europe. Around 45,000 years ago, anatomically modern humans, Homo sapiens, entered southeastern Europe, leaving archaeological traces at sites such as Bacho Kiro Cave in present-day Bulgaria. Stratified deposits at Bacho Kiro contain orignation blade and bone tool assemblages directly associated with modern human remains, establishing a secure chronological framework for their arrival. Radiocarbon dating places these initial occupations between 45,000 and 43,000 BP, coinciding with late Neanderthal presence in adjacent regions. The orignation toolkit spread rapidly across the continent. Blade-based lithics, bone points, and antler implements appear at key sites in Central Europe, France, and the Italian peninsula within several millennia of initial arrival. Stratigraphic continuity and typological consistency suggest that knowledge transmission occurred both within migrating groups and between neighboring communities. This technological diffusion facilitated adaptation to diverse ecological zones, from steppe tundra landscapes in the north to temperate woodlands in the south. Genetic evidence supports a demographic expansion accompanying this migration. Ancient DNA analyses indicate that modern humans largely replaced Neanderthal populations in Europe within 5,000 to 10,000 years, though admixture events contributed 1 to 2% of Neanderthal ancestry to later human populations. Genome-wide comparisons confirm that the influx of Homo sapiens significantly altered the continent's genetic landscape, effectively establishing the basis for modern European lineages. Ecologically, the arrival of modern humans introduced new predatory pressures into Ice Age environments. Hunting techniques, including coordinated group strategies and projectile weaponry, complemented existing megafaunal predation, affecting herbivore population dynamics. Settlement patterns concentrated near river valleys, resource-rich steppe corridors, and cave shelters optimized access to water, prey, and raw materials. Archaeological evidence also demonstrates behavioral flexibility. Occupation sites reveal repeated seasonal use, indicating logistical planning and territorial awareness. Hearth structures, lithic workshops, and tool caches suggest that groups maintained long-term knowledge of local resources and environmental cycles. Such spatial organization allowed human populations to persist in regions previously dominated by Neanderthals, despite climatic challenges. By approximately 40,000 BP, modern humans occupied nearly all ecologically viable regions of Europe. Northern territories, previously uninhabitable due to glacial expansion, became accessible during interstadial periods. In southern Europe, continuous occupation facilitated cultural development, including Upper Paleolithic artistic expression and symbolic behavior. The integration of social networks, tool innovation, and ecological adaptation allowed humans to thrive across a variety of Ice Age landscapes. Movement continued beyond Europe. Reaching Sahul required deliberate ocean crossings. Human presence in Sahul, the combined landmass of Australia and New Guinea during periods of lowered sea level, is documented at archaeological sites such as Majdbeb in Australia's Northern Territory. Excavations at this site reveal stone tools, grindstones, and ochre fragments, with optically stimulated luminescence dating confirming human occupation at least 65,000 years ago. These findings establish Sahul as one of the earliest examples of successful long-distance human dispersal beyond continental Eurasia. During the late Pleistocene, lower sea levels, resulting from the growth of continental ice sheets, exposed land bridges and widened coastal plains. Even so, reaching Sahul required maritime travel across open water channels of up to 90 kilometers. The absence of simple land connections between Wallacea and the Sahul Shelf implies that these crossings were deliberate, planned, and executed using watercraft capable of transporting people, supplies, and tools. This evidence demonstrates advanced cognitive capacities for spatial reasoning, route planning, and risk management. Archaeological assemblages indicate adaptation to diverse environments within Sahul. Stone toolkits at Majdbib include unifacial flakes, grinding implements, and retouched blades suitable for processing plant and animal resources. Residue analysis suggests exploitation of both terrestrial and freshwater sources. Combined with ochre use, these materials reflect both practical subsistence strategies and symbolic behaviors. The dispersal into Sahul also implies flexible social organization. Coordinated navigation, knowledge of seasonal currents, and planning for multi-day journeys indicate that groups maintained complex knowledge systems. These capabilities parallel evidence of coordinated hunting, tool standardization, and long-distance exchange observed in Upper Paleolithic Eurasia, highlighting convergent cognitive and technological development. Paleo-environmental data show that Sahul's interior contained diverse ecosystems, including arid plains, tropical forests, and riverine systems. Humans quickly occupied multiple ecological niches, as evidenced by site distribution across northern, central, and eastern regions. This widespread colonization underscores adaptability in foraging strategies and settlement planning under novel environmental constraints. Cultural markers suggest symbolic behavior accompanied practical adaptation. The presence of ochre fragments and possible ground stone objects at Majdbib parallels contemporaneous Upper Paleolithic symbolic practices in Eurasia. Although direct figurative art has not been preserved, these artifacts indicate abstract thought and planning beyond immediate survival needs. The successful colonization of Sahul represents a milestone in human expansion. It demonstrates the ability to integrate technology, cognition, and social cooperation in navigating complex landscapes. These crossings were not opportunistic but reflect intentional strategies to exploit new territories, contributing to global dispersal patterns. Around 21,000 years ago, global ice coverage reached its maximum extent. The last glacial maximum, LGM, occurring between approximately 26,500 and 19,000 years before present, represents the most extensive and coldest phase of the last ice age. During this interval, continental ice sheets expanded to their maximum thickness, reshaping the northern hemisphere's geography and influencing global climate systems. In North America, the Laurentide ice sheet covered much of Canada and extended into the northern United States, reaching regions corresponding to present-day Illinois, New York, and the Great Lakes. In Europe, the Fennoscandian ice sheet blanketed Scandinavia, the British Isles, and parts of northern Germany and Poland, with ice thickness exceeding 3 kilometers in some areas. Sea levels dropped roughly 120 to 130 meters below present-day levels as water became sequestered in continental ice, exposing land bridges such as Beringia between Siberia and Alaska. This exposure facilitated migration corridors for humans and megafauna, while simultaneously altering ocean circulation patterns. Evidence for lowered sea levels comes from coral reef terraces, submerged coastal features, and global marine isotope records, which collectively confirm substantial shifts in hydrological distribution. Atmospheric CO2 concentrations reached near-glacial minima, approximately 180 parts per million, as recorded in Antarctic ice cores such as Epica Dome C. Lower greenhouse gas concentrations, in combination with orbital forcing, contributed to global cooling. Estimates indicate that mean annual global temperatures were approximately 4 to 7 degrees Celsius lower than pre-industrial levels, with pronounced regional variation. Polar and mid-latitude regions experienced the greatest temperature depression, while subtropical and tropical zones also underwent cooling sufficient to affect precipitation patterns. The LGM was characterized by widespread aridity in subtropical and continental interiors. Deserts expanded across North Africa, Central Asia, and parts of Australia, supported by pollen data and sediment core analyses. Dust deposition intensified worldwide, evidenced by thick loess layers in Europe and China. These aeolian deposits indicate both reduced vegetation cover and stronger winds, reflecting the drier, colder, and more variable climate. Glacial landscapes reached their peak geomorphological impact during the LGM. Ice sheet advances reshaped river systems, carved deep valleys, and created extensive moraines. Glacial erosion sculpted bedrock across Scandinavia and North America, while meltwater during interstadials temporarily reworked sediments in proglacial lakes and lowlands. Ice sheet dynamics influenced oceanic currents by redistributing freshwater input into the North Atlantic, affecting thermohaline circulation and regional climate. Periglacial environments dominated areas peripheral to the ice sheets. Tundra-steppe ecosystems expanded across Eurasia, supporting megafaunal communities adapted to cold, dry conditions. These habitats were productive despite the harsh climate, sustaining herbivore populations such as woolly mammoths, reindeer, and bison. Fossil pollen records indicate open, low-vegetation landscapes with limited forest cover in Central and Northern Europe. Human populations responded to the LGM's extreme conditions through contraction into refugia. Archaeological evidence identifies southern Europe, parts of Siberia, and coastal Asia as major refugial zones. These areas provided sufficient resources and relatively stable climates for survival. Genetic studies of modern populations support this pattern, revealing bottlenecks and founder effects consistent with reduced population size during peak glacial conditions. Marine ecosystems were similarly affected. Lower sea levels and cooler ocean temperatures altered nutrient distribution and productivity. Coral reefs were largely restricted to equatorial regions, while coastal upwelling zones shifted, influencing fish and marine mammal populations. Combined terrestrial and marine pressures forced human groups to adapt their subsistence strategies, focusing on seasonally available resources and high-yield prey. Dust accumulation during the LGM also had climatic feedback effects. High concentrations of atmospheric dust reduced solar radiation absorption, contributing to further cooling, while deposition onto ice sheets enhanced albedo and reinforced glacial persistence. These feedback mechanisms highlight the interconnected nature of Earth systems during the glacial peak. Overall, the LGM represents the climatic and geological apex of the last ice age. Ice sheet expansion, sea level decline, atmospheric greenhouse gas reduction, and widespread aridity defined a period of maximal environmental stress and global transformation. This stage set the conditions for subsequent ecological restructuring, megafaunal adaptation, and human migration. As ice expanded, human settlement zones narrowed dramatically. During the last glacial maximum, vast areas of northern Eurasia became inhospitable due to extensive ice coverage, permafrost, and cold, arid conditions. Archaeological and genetic evidence indicates that anatomically modern humans retreated into more temperate southern refugia where resources remained sufficient for survival. In Europe, these refugia included the Iberian Peninsula, southern Italy, the Balkans, and parts of the Ukrainian plains. Stratified sites such as El Miron Cave in Spain and Puglici Cave in southern Italy provide radiocarbon-dated records of continuous habitation, demonstrating that human groups maintained occupation despite severe climatic pressures. Genetic analyses corroborate this demographic contraction. Mitochondrial DNA and whole genome studies show reduced genetic diversity among populations emerging from glacial refugia, consistent with population bottlenecks during the LGM. These reductions reflect both small group sizes and the isolation of communities, which limited gene flow across Europe. Later expansions into northern territories after the ice retreated carried signatures of these bottlenecks, shaping the genetic structure of post-glacial European populations. In Asia, similar patterns emerge. Human groups persisted in southern Siberia, parts of Mongolia, and temperate East Asia. Archaeological sites indicate adaptation to steppe and forest steppe environments, including specialized hunting strategies targeting cold-adapted megafauna and exploitation of plant resources. Stone toolkits during this period exhibit continuity alongside functional refinement, suggesting the maintenance of cultural traditions despite isolation. Environmental stress within refugia required intensified subsistence strategies. Seasonal mobility was often constrained by ice margins, while localized resources were systematically exploited. Faunal assemblages from southern European refugial sites reveal high reliance on large herbivores, supplemented by smaller mammals, fish, and plant resources when available. Evidence of hearths, storage pits, and site reuse indicates planning and knowledge transmission within groups. Spatial analysis shows that refugial sites were strategically selected to maximize access to fresh water, raw materials for tool production, and shelter from climatic extremes. Cave shelters and rock overhangs provided protection from cold and wind, while river valleys offered predictable sources of food and transport routes. Group sizes likely remained small to medium, balancing resource availability with social cohesion. Interactions between refugial populations may have been limited but significant. Genetic signals of admixture suggest occasional contact among neighboring refugia, contributing to cultural exchange and the spread of technological innovations. These interactions were essential for maintaining knowledge networks and ensuring resilience in harsh environments. The isolation experienced during the LGM also influenced cultural and symbolic behavior. Evidence from lithic assemblages, personal ornaments, and pigment use indicates continued social and symbolic practices, despite demographic pressures. Portable art objects, beads, and decorated tools from southern European sites demonstrate that cultural complexity persisted even under environmental constraint. Post-glacial recolonization of northern Europe and parts of Asia reflects the importance of these refugia. As ice sheets retreated, human groups expanded outward, carrying both genetic lineages and cultural traditions established during periods of isolation. Patterns of tool types, artistic motifs, and subsistence strategies in newly accessible regions often mirror those developed within refugial zones, highlighting their role as reservoirs of human adaptation and innovation. In addition to European refugia, evidence points to analogous survival strategies in the Near East and the Levant. Sites such as Qasr Aqil in Lebanon demonstrate continuous occupation through cold phases, suggesting that human populations utilized multiple geographic corridors to buffer against environmental extremes. These regions provided not only food resources but also connectivity between Europe, Africa, and Asia, facilitating later dispersal events. Overall, the concentration of humans within glacial refugia during the LGM underscores the interplay between climate, ecology, and population dynamics. By restricting settlement zones, glacial expansion created bottlenecks that shaped genetic diversity, cultural continuity, and subsequent migration patterns. These refugial populations preserved technological, social, and symbolic knowledge, forming the foundation for post-glacial human expansion across Europe and northern Asia. After millennia of stability, ice sheets began to collapse. The transition from the last glacial maximum to deglacial conditions commenced around 19,000 years before present, driven primarily by orbital forcing that increased summer insolation in the northern hemisphere. This gradual increase in solar radiation initiated the retreat of continental ice sheets, first at their margins and later more extensively as feedback mechanisms amplified melting. By 16,000 BP, accelerated ice loss reshaped northern landscapes, releasing vast quantities of meltwater into proglacial lakes, river systems, and the oceans. A key event during this interval was meltwater pulse 1A, occurring approximately 14,600 BP. This abrupt influx of glacial meltwater caused global sea levels to rise by an estimated 14 to 18 meters within several centuries. Evidence for the rapidity and magnitude of this rise is preserved in coral reef cores from Barbados and Tahiti, which record distinct layers corresponding to abrupt sea level increase. Simultaneously, proglacial lakes such as Lake Agassiz in North America expanded significantly, storing vast freshwater volumes before episodic drainage events. The discharge of freshwater into the North Atlantic had far-reaching oceanographic consequences. Changes in salinity and temperature disrupted thermohaline circulation, reducing deepwater formation and altering heat transport between hemispheres. Paleoclimate proxies indicate that this perturbation contributed to regional climate shifts, including abrupt cooling episodes in some areas and hydrological adjustments elsewhere. Geological and sedimentary records confirm the impact of deglaciation on terrestrial systems. Glacial moraines retreated, river channels re-established courses blocked during the LGM, and sediment deposition patterns shifted rapidly. Coastal zones experienced inundation, forcing human populations to adjust settlement locations and resource exploitation strategies. Meltwater Pulse 1A represents a clear example of how ice age systems could transition from relative equilibrium to abrupt change. The rapidity of sea level rise underscores the sensitivity of glacial and oceanic systems to small changes in insolation and ice sheet stability. Such events highlight the interconnectedness of cryosphere, hydrosphere, and climate systems during deglacial periods. Paleoecological evidence indicates that vegetation zones responded dynamically. Retreating ice sheets opened new habitats, allowing tundra-steppe communities to expand northward, while forests gradually colonized previously glaciated regions. Herbivore populations followed these shifts, and human groups adjusted hunting and foraging strategies accordingly. The initial phase of deglaciation set the stage for subsequent warming during the Balling-Alarad interstadial, a period characterized by rapid temperature increases and further environmental transformation. The combined effect of ice sheet collapse, meltwater influx, and ocean circulation disruption illustrates the capacity for abrupt change in the terminal Pleistocene climate system. Temperatures rose sharply, reshaping ecosystems within generations. Around 14,700 years before present, the onset of the Balling-Alarad interstadial marked a period of rapid climatic warming following the initial phases of deglaciation. Greenland ice core records document temperature increases of 8 to 10 degrees Celsius over a few decades, highlighting the exceptional speed of environmental change. These abrupt temperature shifts were mirrored across the northern hemisphere, affecting vegetation, hydrology, and animal distribution. In response, forests expanded into areas formerly dominated by tundra-steppe ecosystems. Pollen analyses from Central and Northern Europe indicate rapid colonization by birch, betula, pine, pinus, and later spruce, picea, species. These forest expansions altered habitats for megafaunal species, prompting northward shifts in populations of reindeer, bison, and other large herbivores. Predator-prey dynamics adapted accordingly, with human groups tracking resource availability in newly accessible regions. Archaeological evidence demonstrates human exploitation of these changing landscapes. Cultures such as the Hamburgian, centered in northern Germany and Denmark, show signs of northward expansion during the interstadial. Sites contain specialized lithic tools optimized for hunting reindeer and other steppe-adapted species. Settlement patterns indicate seasonal mobility aligned with emerging forest-steppe mosaics and expanding faunal ranges. Rapid warming also influenced hydrological systems. Melting ice sheets and permafrost released freshwater into rivers and lakes, creating dynamic aquatic environments that supported fish and other resources. Rising sea levels began to inundate low-lying coastal zones, reshaping migration corridors and resource availability. The Balling-Alarad interstadial illustrates the sensitivity of the late Pleistocene climate system. Ecosystems and human populations responded almost immediately to temperature shifts, demonstrating adaptive flexibility and the capacity for rapid recolonization of formerly glaciated territories. This warming period was abruptly interrupted by renewed cooling events. Within a human lifetime, the climate shifted permanently toward warmth. Around 11,700 years before present, the abrupt termination of the Younger Dryas signaled the transition from the Pleistocene to the Holocene epoch. Ice core records from Greenland indicate that temperatures increased sharply within several decades, rising by approximately 4 to 6 degrees Celsius in the northern hemisphere. This rapid warming ended the final cold snap of the Ice Age and established a relatively stable interglacial climate that persists today. The retreat of remaining continental ice sheets accelerated during this interval. The Laurentide and Fennoscandian ice sheets diminished toward present-day Arctic boundaries, exposing previously glaciated landscapes. Glacial melt contributed to continued sea level rise, which proceeded more gradually than during earlier meltwater pulses, but ultimately restored ocean levels to near-modern extents. Geological evidence, including coral terraces and sediment cores, documents the progressive inundation of coastal zones worldwide. Hydrological and ecological systems responded rapidly. River systems reorganized as meltwater discharged from retreating ice sheets, while newly exposed landscapes supported pioneer vegetation. Early Holocene forests expanded across Europe and North America, with birch, pine, and later deciduous species stabilizing soils and creating new habitats. Faunal communities also shifted, with megafaunal populations largely diminished and smaller, more mobile species occupying emerging niches. The Younger Dryas termination represents a formal geological boundary that ends the Ice Age. Human populations benefited from increasingly stable climates, enabling expansion into regions previously limited by glacial coverage. Archaeological records indicate intensified settlement, exploitation of diversified resources, and the development of complex social networks in this warming world. Ecological systems reorganized under new climatic stability. As forests expanded, the mammoth steppe disappeared. The transition to the Holocene brought profound ecological changes across formerly glaciated regions of Europe and North America. Post-glacial warming and increased precipitation facilitated the expansion of forests into landscapes previously dominated by open tundra steppe ecosystems. Pollen and macrofossil records indicate rapid colonization by birch, pine, spruce, and deciduous species, which gradually transformed habitats once occupied by large grazing megafauna. The shift from open grasslands to closed forests reduced the availability of forage for species adapted to expansive, nutrient-rich steppe environments. Megafaunal populations were severely affected. Mammoths, Mammuthus primigenius, woolly rhinoceroses, Coelodonta antiquitatis, and steppe bison experienced steep declines, with most mainland populations disappearing between 11,000 and 10,000 BP. Radiocarbon dating shows that isolated populations persisted longer in refugial environments, such as mammoths on Wrangel Island, which survived until approximately 4,000 BP. The primary drivers of these extinctions included habitat loss due to climatic warming, restricted grazing opportunities, and continued predation pressure from expanding human populations. Human hunting further intensified megafaunal decline. Archaeological evidence, including kill sites and cut-marked bones, demonstrates coordinated exploitation of large herbivores. In combination with rapid ecological transformation, human predation created unsustainable pressures on species that had previously endured glacial conditions for tens of thousands of years. As these animals vanished, humans shifted subsistence strategies toward smaller game, fish, and plant resources, reflecting adaptive responses to a fundamentally reorganized environment. This ecological transition not only altered faunal communities but also reshaped landscapes through changes in herbivore grazing patterns, soil composition, and vegetation dynamics. The disappearance of keystone megafauna initiated cascading effects across ecosystems, influencing plant succession, predator populations, and nutrient cycling. These changes set conditions for new economic systems. Modern geography is, in many regions, a product of Ice Age ice. The retreat of continental ice sheets at the close of the Pleistocene profoundly reshaped Earth's surface. In North America, the Laurentide ice sheet carved extensive basins that would become the Great Lakes. Sediment deposition, glacial scouring, and meltwater drainage created deep freshwater systems, whose modern shorelines reflect the cumulative effects of ice movement and post-glacial hydrology. Similarly, the Fennoscandian ice sheet in northern Europe shaped fjords, valleys, and islands through glacial erosion and deposition. U-shaped valleys, striated bedrock, and moraines in Scandinavia and Scotland provide enduring evidence of glacial sculpting. Glacial processes also influenced soil formation. Fine silt and loess, derived from glacial grinding and wind transport, accumulated in river plains and lowlands across Europe and China. These fertile soils later supported the emergence of agriculture and early civilizations, linking Ice Age geomorphology to human economic development. Even millennia after deglaciation, isostatic rebound continues in formerly glaciated regions, gradually adjusting land elevations as the crust responds to the removal of ice mass. Rivers, lakes, and coastal features established by glacial activity created natural corridors for migration, trade, and settlement. The legacy of these glacial landscapes persists in modern ecosystems, hydrology, and human land use, illustrating the enduring influence of Ice Age processes. These landscapes became the stage for early civilizations. If you found this deep dive into the last Ice Age insightful, subscribe to the channel and hit the bell icon to stay updated with daily Nightfall history videos. Share your thoughts in the comments. What aspect of Ice Age human adaptation or environmental change fascinated you the most? Your engagement helps us explore history in greater depth.